All right, we're starting a new chapter. This will not be on any of our midterm exams, but I'm assuming that it will show up, at least in some form, on the final exam, the ACS exam for Gen Chem. So transition metals and coordination compounds. A lot of this is just new terms to memorize and possibly annoying or fun, depending on how you view it, nomenclature stuff, so naming conventions. The applications of what we're learning about today can be seen in things like rubies, which are red, and emeralds, which are generally green. Those are both caused by the same ion, chromium 3+, the color in those is chromium 3+. It replaces about 1% of the aluminum ions in the crystals. Atoms in the crystal create a field, like an array, where the chromium ions can fit in. This is the crystal field, because it's a crystal. And this splits the d orbitals into 2 or more levels. So the d orbitals are normally degenerate, meaning that they're at the same level, not that they engage in filthy behavior. So they split into multiple energy levels. And because of those differences in energy levels, you can have light get absorbed and cause those to be excited to the higher energy levels, and then those will just relax, and we probably don't see that. But that can cause this change in color, is those energy gaps. They just happen to be in our field of vision. Transition metals seem remarkably similar to each other, to other transition metals, when you compare them to our main group elements. So a lot of them are moderate to high density, they're all metals. They're good conductors, because they're all metals. They have high melting points, because they're all metals. And they have moderate to extreme hardness, again, because they're metals. Right? It's just a bunch of metals, and they're kind of not that crazy different. And they have similar electron configurations, aside from the electron d orbitals. But they're all separate elements, and they have different behaviors. So let's look at the electron configurations to start. If you're moving across a row of transition elements, you're adding electrons to the n-1 d orbitals. So starting in 3d, then next would be 4d, 5d, 6d for our 4 rows. So the n-1 is the row number, n here being row number minus 1 d orbitals. So for example, chromium is in row 4, so it's filling up the 3d orbitals. And typically we're going to have whatever the row number is, S2. So for chromium it would be 4s2, is what we would expect. And then 3d, however many spots we are into that row. There are some exceptions, and these exceptions tend to repeat. So there are exceptions because the ns and the n-1d orbitals are close in energy. And so because of the high stability of half-filled or completely filled orbitals, an s electron gets, as we might call it in the business, yoinked. I don't believe that they call that, they say that in the chemistry business. But I think yoinked is a fun way to talk about it. And so we can see that for chromium. I picked like the worst example for S2. And we can also see that for copper. So with vanadium, we had 3 d orbitals. Or 3 d electrons. We would expect to add 1 more for chromium. But because it's so close to filling out this row, it just goes ahead and steals this this 4s electron to complete that. And because it's half filled, it gains extra stability. And the same thing happens for copper. It's very close to having it all double filled, the d orbitals. And so it goes ahead and grabs that s electron because it gains more stability by it being in the d orbitals and being completely filled versus being in the s. Another note about our transition metals is that they lose electrons from the ns orbital before the n-1d orbital. That's because the s subshell is where our valence electrons are for these configurations. Because they're higher n number. This should be at least partly review. And we can look at our electron configurations for all of our things. We're going to be focusing in on these d block elements. So looking at those exceptions that we saw for chromium and molybdenum. Blue might be good here. For chromium and molybdenum, we've got the 4s1, 5s1, and they're stealing that to get their half-filled d orbital. For our second to last row for copper, silver, gold, all of these are stealing one to get their completely filled d orbitals. Tungsten and Sg seaborgium don't do that stealing effect for some reason. But generally, we get that stealing one to finish out the row or finish out the subshell. All right, let's write ground state electron configurations for osmium and niobium-2 ion. First thing we need to do is find where they are in the periodic table. So osmium is number 76. It's in group 8, period 6. So it's in period 6. We're going to start with our shortcut. Going to row 5, we find xenon is our noble gas. We can use our noble gas shortcut. Xenon in brackets, that represents all of the electrons up to xenon. The next thing that would come up would be the 6s orbitals. So 6s, we are well past 6s, so we've got 2 electrons in there. And then next comes our lanthanides. So right after barium, we get to lanthanum through lutetium. Those are our F block orbitals. So that's going to be 4F14. Because we're past it, there's nothing weird about it. It's just that it's n-2 instead of n-1. So 4F14, and then we are 1, 2, 3, 4, 5, 6 spots over. So I believe we should be 5d6. And we can check that. This is 54 electrons. Osmium in its ground state should have 76 electrons. So we're expecting 22 electrons. We placed 2 in the 6s. So we've got 20 left. We used another 14 for our F block. And then we used the final 6 in the D block. Questions about that? All right, go ahead and write the ground state electron configuration for Nb2+. All right, our Nb2+, we're finding Nb on the periodic table. It's in period 5, or row 5. Our row 4 noble gas is krypton. So I'm going to write a very bad K and then an R to represent krypton. It looks like her. And then we're going to proceed to row 5. We're starting off with our 5s2. We're just doing the ground state for now. ground state, neutral. So 5s2, and then our 4, yes, our 4d, and we're in the third position, 4d3. This would be our ground state. And then we need to remove 2 electrons to get Nb2+. So we're still going to have krypton, much better K. Where do we remove our 2 electrons from? 5s or 4d?
5s.
We remove them from the 5s. So it'd be krypton, shortcut, and then 4d3. I'm pretty sure we don't need to write 5s0. Okay, so that's a review of electron configurations. We've got a bunch of periodic table trends. A lot of this should also be review. Atomic size is one of our trends. We're looking this time specifically at our transition metal elements. So when we're looking across a row, moving left to right on the periodic table, after the first 2 elements, we don't see very much difference in size. This is because the number of electrons in the outermost principal energy level is basically constant. So the number of electrons in the s orbital is basically constant, and so the distance from that outer shell to the nucleus is about the same the whole way through. For the first couple, though, we're adding those electrons in, and so there'll be some changes from that. The effective nuclear charge is also roughly constant. It does increase a little bit as we move left to right. Moving down a group, our second row is larger, but there's no size increase for our third row. So general trends still hold. Bigger things are on the left. Things also get bigger as you go down, but there's some big exceptions to that. For ionization energy, we're looking at removing an electron from the gas state. So across a row, moving left to right, it increases as we would expect. So things that are further on the left, it's easier to remove an electron from. Things that are on the right, it's harder to remove an electron from. If we move down the group, so moving down rows, our third row is actually higher ionization energy than our first 2 rows. And this has to do with the charge. So the charge of our nucleus is substantially higher if we look at tantalum versus niobium. Tantalum has 73 protons. Niobium has 41 protons. So this is comparing our row 2 versus our row 3 in our transition metals. So 41 compared to 73 is a vastly different amount. Right? It's not double, but it's pretty close to double. And so having 73 protons, those outer electrons are going to be held a lot more tightly. So it's going to be a stronger pull or hold on our outer electrons because of those increased protons. For electronegativity, we also expect it to increase to the right and up as we're moving towards fluorine. So if we're moving across a row, it increases as we expect. Moving down a group, though, we get the opposite trend. It increases from the first to the second row, and then there's no change for the third row. So we would normally expect it to decrease as we move down. This has to do with the small size change with a large increase in nuclear charge. So it's a similar property to what we saw with ionization energy. Similar idea. And then something that's new, oxidation states. There's a lot of oxidation states. There are many such examples of these. oxidation states. Many possible oxidation states. And to me, somebody who's not an inorganic chemist, the annoying part of inorganic chemistry was having to memorize a lot of these. Memorizing or knowing the different options for ions for a lot of different transition metal elements. Our highest number, our highest transition metal is a +7 for manganese here in the middle. So we can get a +7, and then everything else, it's kind of pyramid looking in terms of its highest ionization energy, not highest oxidation state. And these, so we're looking at our oxidation states on our y-axis increasing as we go up, and then looking across the first row of, just the first row of transition metals. All of these highest oxidation states are noble gas configurations. So all 4s and 3d electrons removed for our maximum. And then the metals that are to the right of manganese have mostly just +2 and +3. And the reason that +2 is so popular, pretty much all of them except for scandium has it. The reason that +2 is so popular is because that is the loss of your ns electrons. So pretty much all of them will do that. Some of them will also remove others. Any ideas why copper might have this +1 as an option when none of the others do?
It's like an odd amount, like in the, I forget what it's called, like for the spin part, like 3 up arrows, 2 down arrows or something. So it gets like rid of one of them to make it more stable.
Yes, that idea is partially correct. So remember, copper has that, it's that weird exception where we expect it to be 4s2, 3d9. It yoinks one of those s electrons, and so it only has one electron in its 4s orbital. And so that's the reason, presumably, why it can form this +1. We're just removing that one s electron. Why it doesn't happen in chromium, I don't know. Chromium, for some reason, is not down with that, but copper, perfectly fine with it. Anyway. All right, moving on to the fun or annoying nomenclature parts of stuff. So transition metals can form a bunch of different compounds. We would generally call some of these coordination compounds. So transition metals can form complex ions. We're looking at a complex ion here on the left side of this diagram. It contains a central metal ion bound to one or more ligands. Ligands, ligate, just means like to stick, I think. So they're just things that are stuck to, in this case, our cobalt. These are Lewis bases, and they do form a bond with the metal, but it's not exactly like the bonds that we think of before. It's really because they're Lewis bases. Who remembers what a Lewis base is?
Is that where it wants to like get rid of an electron or something?
Yes, it's where it wants to donate an electron pair. This was our last definition of acids and bases that we learned. So Lewis thinks about the electron pairs, donating an electron pair or receiving an electron pair. So our ligands can donate an electron pair to the central metal ion. And that whole formation is our complex ion. A coordination compound also has counter ions that are just there basically for charge balance. So our coordination compound is a neutral compound. It's got a complex ion and it's got some counter ions so that the whole thing overall is neutral. Our metal ion has two types of interactions. It's got a primary valence. The primary valence is the charge, basically, I think it works for charge, the charge on the metal center. So inside of this complex ion, what's the charge of our ion, our metal? And then we've got a secondary valence, or a coordination number. And this is how many ligands are attached. So for example, for this compound, we've got our complex ion in brackets and our counter ions on the outside. This whole thing together is a coordination compound. Our primary valence, we need to figure out what the charge is on our cobalt. Our ammonia groups that are ligands that are coordinated with the cobalt are neutrally charged. So these are not going to affect our charge. So then we have to look at our counter ions. Our counter ions are chloride. Chloride has what charge? -1. So those will be Cl minuses. We've got 3 of them, so we'll have 3 minuses. That means we've got 3 minuses balancing out our cobalt, so our cobalt must be 3 plus. So 3 plus would be our primary valence. Our secondary valence is how many ligands are attached to the cobalt. Any ideas? It's 6. We've got 6 ammonias. We've got 6 NH3 groups on cobalt. So our secondary valence is 6. You can also have these other coordination compounds that are related. They're not exactly the same. So some of those chloride counter ions, for example, might make their way in, swap out one of the ammonias, and form a different coordination compound. So our complex ion, in this left example, we'd have 5 ammonias and 1 chloride. That's going to have a different primary valence. No, it's not. It'll have the same primary valence and secondary valence, but it's going to be a different compound. We could also swap out 2 of these ammonia groups for the chlorides. So our Cl could replace the ammonia. It can act as either a counter ion or a ligand. Questions? How much fun are we having so far? It gets better, don't worry. Better is and more fun. This will not be on our test today. Presumably it will be on the ACS exam. Okay, so a coordination compound, a complex ion, is a Lewis base adduct. They're stuck together. The Lewis acid part being the metal, the base being the ligands. So the coordination bonds, those bonds form when the ligand donates a pair of electrons. That's Lewis base behavior. To an empty orbital on the metal. Since the metal is receiving the electron pair, it's acting as an acid, a Lewis acid. and that forms a coordinate covalent bond. They're sharing the electrons. So Lewis bases are electron pair donors, and ligands are good Lewis bases and have at least one lone pair. You have to have a lone pair to donate a lone pair. Can't give away money that you don't have. Atoms and molecules don't have credit cards. All right, so some examples of common ligands seen here. It's a little small. We can zoom in. So some ligands that we could have things like water, ammonia, chloride. We can also have slightly more complicated things, carbon monoxide, cyanide, thiocyanate, the sulfur here contributing this thio part. We can have even bigger things like oxalate that looks like this. Notice that all of these have lone pairs. They have to have lone pairs in order to function as a Lewis base. They get even bigger. We get things like ethylene diamine, and the biggest of the ones that we'll look at today, ethylene diamine tetraacetate, EDTA. I'm expecting that you won't have to memorize this structure of EDTA. You'll just need to know some properties of it. You'll have to recognize the name. And there's a couple of pairs here that are lightly in red on EDTA. All 6 of these lone pair groups can donate as Lewis bases. So some of our shortcuts, OX, EN, and EDTA for oxalate, ethylene diamine, and ethylene diamine tetraacetate.
So do we have to memorize those ones? Like the ones other than that, EDTA?
You should recognize the name. I'm not 100% sure if you need to know the formula. It would probably be a good idea to recognize the formula for ethylene diamine and oxalate. Oxalate's easy, C2O4, 2 minus. So the reason that we looked at some of those red electron pairs is to talk about denticity. So within our ligands, we've got monodentate ligands. Monodentate ligands, the mono means that they donate one pair of electrons to the central atom or the central metal. We also have bidentate ligands that donate 2 pairs of electrons from different atoms. And our 2 bidentate ligands are oxalate and ethylene diamine. When you go to the dentist, what does the dentist look at? Your teeth. Dentist, teeth, dent, teeth. Dentate, teeth, al dente, to the teeth. So this is 1 bite, 2 bites. 1 tooth, 2 teeth. Polydentate, many teeth. So this is just the number of teeth, basically, that they can get into the metal center, the central metal atom. Our polydentate ligands donate more than 2 pairs. And our ethylene diamine tetraacetate would be 6 or hexadentate. I don't remember which one it is, but that's polydentate. Any questions about toothiness
So that's just
among
what's
ligands?
attached to the central ion?
Yeah, it's just about how many lone pairs can they donate.
So would the nitrogens be central, or would those be considered dentate?
The nitrogens here,
Yeah.
these are both the each of those would be contributing one lone pair to the central atom. So it's always going to be a transition metal in the center.
Okay.
So this one, like if we were to draw it out, let's do it in 2D because that's easier. One of those could donate, let's say, from the bottom. And because we've got 2 carbons on here, we can get a little bit of a wraparound so that the nitrogen can get over from the side. So it'll latch on kind of like an arc shape to take up 2 spots on our, however many we'll have for our central atom. And I'm omitting the hydrogens for brevity. Okay, so EDTA gets all wrapped up around this metal. We've got an example of what that looks like down here on the right with cobalt 3+. It's a little bit hard to see all of the centers, but we've got a bunch of oxygens. We've got 4 oxygen groups. So 1, 2, 3, 1 below, and then we've got also these nitrogen groups. So it's very busy, completely wraps up the transition metal center. And we would also classify this as a chelate. This is the same sound as in chemotherapy. Hopefully you know that it's pronounced chemotherapy and not chemotherapy. I think it's Greek, but I didn't look it up. I thought about it on my way here and I was like, I should not look things up in the dictionary while I'm driving. So a chelate is a complex ion that contains a bidentate or polydentate ligand, which is the chelating agent. Chelating agents are nice for some uses because since they have 2 or 6 or however many binding sites, once they get attached, it's really hard to remove them, which can be bad if you want to remove the central metal ion. But if you're trying to bind it up and pull it out of solution, chelating it is a great way to do it. So if we, for some reason, wanted to remove a lot of cobalt-3 ion from our solution, throw some EDTA in there, and that should bind it up and remove it from our solution. There's instances where this is useful. Take organic or inorganic chemistry if you want to learn more, or read just stuff on the internet. Okay, so coordination numbers, the number of ligands that we can have, or number of ligand sites, can vary from 2 all the way up to 12, but our most common are going to be 4 and 6. The coordination number is going to be 2 if you've got a 1+ ion. Generally, though, 4 or 6 is going to be our go-to. So we can have 4 monodentate ligands to 6 monodentate ligands, or we can have 2 or 4 bidentate ligands, where we can have 1 EDTA. The geometries, the shapes, depend on the number, the coordination number, how many sites we have, as well as the number of d electrons in the metal ion. But generally our shapes are going to be square planar and tetrahedral and octahedral. Those will generally be our shapes. So square planar, I would guess for square planar, we've got some extra lone pairs. One's going up, one's going down. For tetrahedral, we don't have any lone pairs. So we get 4 groups evenly spaced around our central metal ion. Now the fun part, naming coordination compounds. Step 1, you want to name the ligands. So all the different groups that we have. This whole long honking thing is ethylene diamine, typically shortened as EN. Generally, we'll give them molecule naming, but we do have some exceptions, like H2O is aqua, NH3 as amine. So we've got 2 M's instead of ammonia. CO is carbonyl. And this is for neutral ligands. So for neutral ligands, we're going to name them like this. For anionic ligands, we use the name of the ion plus these changes. The ide ending becomes O, so Cl- is chloride, it becomes chloro. The ate and ite endings become ado, or ato and ito, something like that. So SO4 2- is sulfate. As a ligand, it's sulfato or sulfato. You can tell that I've not spent much time around inorganic chemists since I don't know the correct pronunciation. And then SO3 2-, 1 less than 8 is ite. So SO3 2- is sulfite, sulfito. So that's all good and fun. Okay, so that's our ligands. And when we're listing them out, we list the name of the ligands in alphabetical order. Ligands in alphabetical order before the metal. So for example, NH3 amine is listed before chloro, which is listed before nitrito. Since A comes before C and C comes before N. So that part of it at least is not too crazy. We can also use prefixes. So we're going to use the prefixes that we know and love from molecular compound naming conventions. Di, tri, tetra, penta, hexa, etc. So we use a prefix for number of that particular ligand. And we've got some new ones. So for example, ethylene diamine already has a di in it. And so to not get confused, like if we had 2 ethylene diamines, diethylene diamine, could be, maybe we've got 2 ethylenes in there somehow. And so we get some special other prefixes. So we've got bis, tris, and tetrakis. That we can use for things like ethylene diamine. So bis is 2, tris is 3, tetrakis is 4. And I just love the way that that sequence like rolls off the tongue. Bis, tris, tetrakis. So for things like ethylene diamine tetraacetate, other ligands that have those di or tri in them, we have to use bis, tris, or tetrakis in front of the name, and the name the ligand gets put in parentheses. So that's new and weird, but it's also cool and fun. And then we get to name the metal. So when the complex ion is a cation, which is usually what it's going to be, use the name of the metal, followed by the oxidation state written with a Roman numeral. Remembering that complex ion is metal plus ligands. So our metal is always going to be positively charged. We could have neutral ligands, we could have negatively charged ligands, we could have a mix of both. So if the complex ion, the metal plus the ligands, is positively charged, then the naming is what we're used to. So CO3 plus is cobalt 3, Pt2 plus is platinum 2, copper plus is copper 1. If the complex ion is an anion, so if we've got extra, like if we've got negatively charged ligands, and the overall charge for that is negative for our metal plus negatively charged ligands, then we add the 8 at the ending. So cobalt 3 turns into cobalt 8. Platinum, we drop the and that turns into 8. Platinate. Copper changes to its Latin root cuprate. I'm guessing that on an ACS exam they wouldn't give you copperate and cuprate as different options with everything else being the same. So the tricky part would be probably not for copper, wouldn't be too tricky. You might see cuprate and be like, oh, that's copper. But for things like tin, I'm pretty sure it's not tinate, it's stanate. It's the SN is stanate. And then you can write the entire name of the complex ion by listing the ligands first, followed by the metal. So we're going to collect our pieces and then put them all together. So PT, NH3, 2, Cl4 with an overall 2 minus. We've got amines, we've got chloros. We've got 2 amines, so diamine. The di because of that 2. The amine or amine because of the NH3. And then we've got tetra, because we've got 4 chloros. Chloro, because it's chloros. And then platinate, because we've got 4 1- charges from the Cl4. Overall charge of 2 minus. Platinum would have to be a 2 plus. What color have I not used? Orange, go Tigers. So that's a rough breakdown of the parts of that name. Questions about naming coordination compounds? All right, more tables from our book. So table 26.5 might be helpful. So looking at metals and the name if they're in an anionic complex, since if they're in a cationic complex, they're just what we expect to see. So the ones here that are maybe a little bit weird, gold is aurate, iron is ferrate, lead is plumbate. Other ones, silver is argentate, tin as stanate. I think those are probably the weird ones. So this is more just a, hey, you should recognize these. These ones are the Latin. I don't expect you, personally, I don't expect you to have these all memorized. It's more of like you should be able to recognize, hey, I need to do a name change. I should go look at a table to figure out what the name change is going to be. When we're writing the formula for a complex ion, write the symbol of the metal first, then write the neutral molecules, and then the anions. So if we're working from a name to a formula. So name to formula, this is what we're doing. Metal first, then neutral, then anions. And these also go in alphabetical order based on the chemical symbol for if we have multiple types of neutral ions or multiple types of anions, specifically things that are acting as ligands. All right, time to have some fun. Let's name the following compounds. So we want to figure out what ligands do we have. So in this first compound, our complex ion is in brackets. So this is our complex ion. We've got two different ligands. We've got CO. CO is carbonyl. We also have NH3. NH3 is amine. How do we choose which ligand goes first in our name?
Alphabetical.
It's alphabetical order based on the name. So amine is going first. How many amines do we have?
5.
We have 5. So pentaamine. Pentaamine. I don't think we use a mono prefix. So pentamine carbonyl. And then our metal name. So looking at this complex ion as a whole, is this going to be positively or negatively charged? What's our counter ion in this example? What's not part of the complex ion? SO4. Our counter ion is SO4. What charge does SO4 have as an ion? Yeah, 2 minus. So SO4 2 minus. That means that our complex ion is 2 plus. So we've got a positive complex ion. And so our naming is just the name of the metal with its oxidation state or its charge number in Roman numerals. And I'm pretty sure we also put a sulfate at the end, of course. Questions about that one? All right, and then our other one, we've got a smaller complex ion. our complex ion is PtCl4. Cl takes the name chloro. We've got 4 of them, so we give it the tetra prefix. And I'll start with naming our counter ion. So we get sodium, and then moving on to our complex ion, sodium tetrachloro. And then we need our metal name. Pt is platinum, but what is the charge on our complex ion, positive or negative?
On platinum or on the complex ion?
The complex ion overall.
Positive.
What charge does sodium have as an ion?
Plus 1.
+1. So our PtCl4 overall has to have a negative charge. Okay, so the charge breakdown. Na2 gives us a total of 2+. That needs to be in balance with our PtCl4. So overall, PtCl4 has a 2-. So the balance between platinum and the Cl4 has to equal an overall of 2 negative. What's the charge on chloride?
-1.
-1, and we've got 4 of them. So we've got 4 minus. Platinum needs to be whatever makes up the difference, which is +2. So platinum has a 2+ charge. Questions about that? Okay, so it's negative charge on our complex ion, so the metal gets the 8 ending. So change the ending of platinum to 8. And the charge we determined was 2. So sodium tetrachloroplatinate 2.
And why is it 8?
It's 8, the ATE ending, because the complex ion has a negative charge. So this PtCl4, the stuff in brackets, overall has a 2 negative charge. Since it has a negative charge, that's when we use the 8 ending.
Okay. And then how come we didn't use like bis, tris, or tetrakris for the first one?
In the first one, we don't have anything that has di, tri, tetra, etc. in it. For the stuff that we've covered in this class, it's only going to be ethylene diamine or ethylene diamine tetraacetate, EDTA,
Okay.
that we use bis, tris, tetrakis. So that's a very fast overview of the naming. We also have a lot of stuff that goes on with the structures. So isomers have the same formula but different structures. Ooh, that's a bad color. That works better. Same formula but different structures. And there are many types of isomers. Generally, we've got structural isomers and stereoisomers. So structural isomers have different connections. It's like we've switched up like what's in the chain. So let's say, for example, that we've got some compound that's got a carbon bonded to a carbon bonded to a nitrogen. We have a different compound that's got the nitrogen in the middle. Those would be structural isomers, different structures. our stereoisomers just have different orientations or rotations, which I can't do a good example of with this CCN versus CNC, but we'll see examples of this. So they're connected the same way. They would all be, for example, CCN or CNC, but other parts that would be coming off of them would be arranged slightly differently. We'll see many such examples of these. I think we're focusing primarily on stereoisomers. Okay, we can have some structural isomerism, so changing the connectivity. A coordination isomer is when coordinated ligand exchanges place with an uncoordinated counter ion. So our counter ion and ligand swap. So our example being in this left compound, we've got a bromine that's a ligand and a chlorine that's a counter ion, and they swap places. So the bromide is now the counter ion and the chloride, or the chloro group, is now the ligand. It's the same formula, it's the same number of atoms, but we've swapped two of the pieces. So the counter ion, instead of being outside, is now inside, and the bromide is outside. We can also have linkage isomers. So a different atom in the ligand is bonded or coordinated to the metal. And I think we've got examples of that coming up. Yes, linkage isomers. So just look at this table 26.6. We've got a couple of different ligands. We've got 4 different ligands. This ONO, if we're bonded to this oxygen on the end to our metal center, it's nitrito. If we're bonded to the nitrogen, that would be nitro. For our cyanide group, if we're bonded to the carbon, that's the cyano. If we're bonded to the nitrogen, that's isocyano. So you can imagine how fun naming can be with all of these different names. I'm sure that there's a great way to remember all of them. I don't know what it is. Mostly the trouble comes from which group gets the iso or nitrito versus nitro. So these would be examples of things that could form linkage isomers, because you could either have the cyano part or you could have the isocyano part bonded to your central atom. And these do actually have different colors. So if we look at nitro bonding, so bonded to the nitrogen, all the nitro groups on the carbon, or on the cobalt, sorry, we get this like orangey color. We get a darker orange color if we're bonded to the oxygen, the nitrito. And that's just for this bottom group here. So that causes a different splitting of the d orbital energy levels to change the color. Questions about our structural isomers? It's all very good. It's all very fun. Smile. Okay, stereoisomers, which I think in many ways are easier, probably because they also show up in organic chemistry, some of these terms. So we can have geometric isomers. So these have different spatial arrangements, different geometries. So cis-trans isomerism can occur in square planar complexes. So cis means same, trans means opposite. So on a cis isomer, the chloro groups are on the same side, the amine groups are on the same side. For trans, they're on opposite sides. So the amines are opposite each other, the chloros are also opposite each other. Cis, same, trans, opposite. It can also occur in octahedral complexes, so where we've got 6 ligands or 6 groups on the central atom. So looking at an example of cis, we've got some chloros. They're on the same side or on corners next to each other, and then the trans isomer, they're opposite each other. They're not possible in tetrahedral complexes just because of the shape. They're all adjacent to each other. You won't always have cis-trans isomers. Other examples of isomers are Fac-Mer isomers. So these can occur also in octahedral complexes where you have got 3 of one ligand and 3 of another ligand. So Fac for facial, like a face on a die or on dice. So if you were to connect all 3 of these chloro groups, all 3 of these amine groups, all the parts that are connected, you'd have octahedral 8 sides. And all these chloros make up the corners of one face of that die. And the amines make up one face of that die. They would be 3 corners of one face of your D8. And then Mer is meridian. That's the other option. Along a meridian or in an arc. You can think of them as all lined up on, I don't remember what the name is now, but like on a globe, you've got the lines that run north-south, spaced all the way around the globe. And like you've also got ones that go east-west that are like Tropic of Cancer or whatever. Think of it as being lined up along one of those north-south lines. So you've got one on each pole, and then you've got one at the equator, kind of as an arc around the globe. And then you've got another one that's doing that, but just rotated. So that's the difference between our Fac and Mer isomers. And we will get to this fun for drawing structures and labeling the types of all the isomers of each of these complex ions on Wednesday.